Hello, and welcome back to, for now, what is the final video in this collision series. First and foremost, I would like to apologize for the delay. Again, two hurricanes in Florida, a faulty power supply, and a healthy amount of tunnel vision in unrelated areas of the project really put me behind on this one. However, luckily, there is not much to go over, as most of what I can say is already said by Dirk in his GDC talk, which this code is based from. And truth be told, I think it's actually far easier to understand what we're doing today with the visuals and demonstrations he provides in his talk. So I would highly recommend you watch his first, link below, before proceeding. Now with that being said, let's begin. Beginning here in the query face direction, we are looking for the point which minimizes the distance from a reference plane on one convex hull to another. So to do this, we loop over all the faces of one hull, and then we find the support point of the other hull, and the support point is gotten using the local direction of the searched hull. This requires the face plane to be transformed into world space, and then transformed into the local space of the hull, which we are searching for the support point for. The distance is simply the dot product of the plane and the point, and we keep track of the most negative distance. Also, we check if we find a positive distance, we can exit early as the objects are not colliding. Finally, we return the face with the most negative distance. We'll be looking at the edge query, which will be using the Gauss mappings of the edges, which are essentially projections onto a unit sphere using the vertex normal of the plane associated with the two edge faces. So to do this, we first loop over the edges of hull 0 and derive its Gauss mappings. And then for each edge of hull 0, we repeat that process for the edges of hull 1, deriving their Gauss mappings. Then we test if the two edges make a face on the Minkowski difference. If so, we compute the distance between the edges and likewise keep the most negative distance and exit early if a positive distance is found. Then finally we return the edge pair with the most negative distance. To derive the Gauss mappings, we first want to compute the edge itself, and then this edge becomes the arc on the unit sphere. Once we have the arc edge, we'll also want to compute the points on the unit sphere by transforming the normals of the face planes conjoining the edges into world space. And I believe I misspoke earlier, it's the face normals, not the vertex normals. To check if we have a Minkowski face, we want to ensure that the great arcs intersect, and we also want to make sure that they are on the same hemisphere. And in order to do this, we can leverage the scalar triple product we've been using in the last few videos in order to check for this separation. And finally, to compute the distance for edges, we'll first find the cross product of the two edges in question. And then after assuring that the edges are not parallel, we use the magnitude of the cross product and compute the normal direction. We then do a check to make sure that the normal is oriented from the first hull towards the second and adjust as needed. And finally, the distance is the dot product between the normal and then the direction from the edge vertex 0 to edge vertex 1. So moving on to contact generation, we'll begin with faces. We begin by finding the most anti-parallel face to the reference hull on the incident hull, and this is done by comparing the normals of the two hulls. Next, we collect the incident edge vertices in world space, And then after we have the vertices, we'll clip them using the Sutherland-Hodgman clipping algorithm, and this generates a set of potential vertices. With each of the newly created points, we project them onto the reference face, and then after the projection, we refine the contact points. One addition to the code I had to make was after point refinement, I had to remove any points that were not too far above the tolerance threshold. Again, this was not in Dirk's slides, but I can't see anything obviously wrong, and the code does seem to work fine for now. In order to refine the contact points, we are looking to reduce the set to 4 points which maximize the contact area. So the first point will simply be the most extreme in some direction. The second point is the one with the largest distance from the first. The third point will be the one which maximizes the triangle area. And then the fourth point will likewise be the one which maximizes, this time, the quadrilateral. And a note to be made about this fourth point, we check to make sure that the winding area is negative, as we want to add a point outside the current triangle. Now, converting the face contact is very simple. We're just interested in computing the contact data needed for the solver. So this will be the normal, which is the normal of the whole face, the interpenetration, which is the distance computed from the face query, and then the contact points are the refined contact vertices. Moving on to edge contact generation, which is far easier than the edge query, we use the two edges in contact and compute the vectors describing the edges in world space. We then find the closest points on the edge segments and set the collision point as the center of the resulting points. The separating axis is then calculated similarly to how the edge query is done and ensures proper normal orientation. And then edge conversion, again, very simple. The collision point is the midpoint, interpenetration is the query distance, and then the normal is the separating axis. And with that, that is all for today as far as the separating axis for convex polyhedra is concerned. Thank you all so much for sitting through and waiting out this collision physics series. I will be putting a pin in it for now. The decomposition algorithm I want to take another look at, as well as the resolver. I don't understand it to a degree which I feel comfortable to present it. However, with that being said, what we'll be focusing on next is what took most of my attention away from finishing up this final video, which is moving into the AI engine of Manifest, which that is more of an area of active research, if you will. So that'll be done more in a devlog style, but I am very excited, and I hope to see you in that journey. Thank you, and have a good day.